Hey folks, welcome to this episode on orbital hybridization. This time we're going to be talking about pi bonds. So when we look at a structure called ethene, or sometimes it was previously known as ethylene, there's a double bond that is formed between the carbon atoms here. So when we saw ethane before, that would have three hydrogen atoms with a single bond, but ethene has this double bond. Now, when we look at this obviously is created to satisfy the octets of the carbon atoms. And when we look at this, we can look at its hybridization. So because this carbon has three electron domains, 1, 2, and 3, we know that it's going to be sp2 hybridized. So again, it has three domains. The s1, p2 will equal to 3. So when it looks like this, we also have a trigonal planar geometry, which is about 120 degrees. Now, as we mentioned before, the presence of this double bond will actually take up a little bit more space and push these ones a little bit less. So this 120 will be a little bit less, but for the most part, we're going to call it 120 degrees. Now, when we look at this, the sp3 hybridized orbitals, they will overlap over here. So if we kind of draw it over here, you'll have an sp2 hybridized orbital. You'll have that. Same thing with the carbon, carbon, carbon. So you're going to have some overlap between these carbons, and that's going to create that single bond. And then when you have your hydrogens, there's going to be some overlap over here, and those are going to create your sigma bonds between your carbons and your hydrogens. But the question is, how do we get this double bond? How do we get that double bond? Because the sp2 hybridized orbital is already engaged in a sigma bond between the two carbons. So let's talk about that bond. When we talk about double and triple bonds, they're actually created by the overlapping of p orbitals, so unhybridized p orbitals, and this results in something called a pi bond. Now, the pi bond, when we look at it, it actually occurs over the sigma bond that's created. So if we were kind of just drawing that ethene before, we had that carbon that had a bond there, we had hydrogen, hydrogen over here, and here. So what happens is that this is going to be your sigma bond over here. There's going to be that little overlap. That's your sigma bond there. And the actual double bond that's being created occurs above and below the actual sigma bond. And this is why we don't actually care about the pi bond when it comes to figuring out its geometry, because the hybridization of those single sigma bonds will determine the hybridization and therefore determine the shape of that molecule. So when we look at this, you'll see that they kind of overlap and they'll kind of move closer to one another and eventually kind of overlap just like that, creating this kind of area that you have over here. Now, when it says here, we have one set of p orbitals. So this is one set. So here we have the kind of two lobes of each p orbital. That's one set. If we were looking at one set, we would create a double bond. So we already have a sigma bond in existence, and when we pair this setup, we're going to have a double bond. Now, for a triple bond, you'd actually need another set of p orbitals, and then these ones would bond up as well. So you'd have bonding between these p orbitals that exist there, you'd have bonding in the sigma bond, and then you'd also have bonding in the other set of p orbitals, unhybridized p orbitals. And when you have two sets of p orbitals, that's when you're going to have a triple bond. So obviously, in terms of ethene, if we need to have a p orbital or an unhybridized p orbital, we have to show that hybridization is such. So here's our ground state of carbon. Okay, we have our two valence electrons. Now, we need to leave an unhybridized p orbital for it to engage itself in a double bond. So we have to go into an sp2 hybridization. That's the only way. And that also now explains that the trigonal planar geometry. Okay. So that's that trigonal planar geometry, and then this one will create that double bond. So one of these will be bonding to the carbon. One of these and one of these is going to be bonding to the hydrogen because we have the two hydrogens coming off of that carbon, and then this one is going to be involved in the double bond with the other carbon. So this is what the structure would look like. So once again, you have your sp2 hybridized orbitals. And so you have one here, you have one here, and you have one here. So again, that's when you look at the other carbon, that's the overlap, and that's going to be your existing sigma bond. So remember, the sigma bonds are a lot stronger than your pi bonds because they're a head-on interaction, where these ones, they kind of have to move over, and there's a greater distance between the carbons. You can see that the geometry doesn't allow them to really move on to a head-on interaction. So they create this pi bond above and below. So in this case, this is your unhybridized p orbital of the carbon, and your 3 hybrid orbitals sp2. Same thing with this carbon, you have your sp2 hybridized orbitals, and you have your 1 unhybridized orbital here. So kind of a side view over here, you can see that these p orbitals stand up straight up and down from the structure, which is a planar structure. You already have your existing sigma bond, and then you create these kind of actual pi bonds there when they actually overlap between the two. One thing to talk about is rotation. When we have a single bond, for example, and this is ethane, you can see that we have our single bond. This is all of these are going to be sp3 hybridized. Okay, so they have 4 electron domains. Each carbon has 4 electron domains. So it's going to be sp3 hybridized, and that means that this bond is going to be a single bond over here. Now, if you look at the orientation, you can see that this bottom side doesn't change, but you can see the top side is actually flipped 180 degrees. And that's because whenever you have single bonds, any single bonds between these hydrogens or whatnot, this can actually rotate amongst itself. And it can create any kind of shape. And it does it freely when it's in 3D space. It doesn't require any energy. It's just moving around and it's rotating naturally. However, when you introduce a double bond, you actually you restrict that rotation now. And what you actually get is you have your pi bond here. So when it's trying to rotate, you can kind of, if you draw it this way, this carbon-carbon bond, this carbon will not be able to rotate because it actually now has another thing that's holding it together. And so you won't be able to create a rotation. Now, an important thing arises from this. If you look at where these groups are, you can see the CH3, they're on this side over here. They're all both on the same side. And when both of these functional groups are going to be on the same side, we call this a cis isomer. Conversely, when we look at here we have the CH3, and then on the opposite side we have our CH3 with a double bond. We call this a trans isomer. Now the reason we differentiate the two is because you can't have any rotation. So once this is on that side, it will always stay on that side. Now, obviously you can add a little bit of energy, and the pi bond can actually break, and you can move this back onto this side, like rotate the bond here and move it on over here. But generally, we assume that it's not good, that rotation is not going to happen, and they're going to just be staying on opposite sides. So when we look at something called ethyne, and this is the structure, the Lewis structure for ethyne, you can see that here we have a triple bond. Now again, we have to have a sigma bond in existence, and that's going to be our sigma bond. But then we have a double bond and a triple bond. So we have to explain this. Remember that a double bond occurs when there is an unhybridized p orbital. A triple bond occurs when there's 2 unhybridized p orbitals. So our hybridization of carbon, again, here's our ground state. We have to create two sigma bonds. That's going to be from the sp hybridization. So 1 sigma bond here and 1 sigma bond to the hydrogen. And then we have our 2 unhybridized p orbitals. And one of those is going to create the double bond, and the other one's going to create the triple bond. So again, both carbons involved in this will have this hybridization. Both carbons will bond to one hydrogen. Both carbons will bond to the other carbon, and then they will create a double and triple bond over here. So again, here's the structure of ethyne. You can see here, and this is our carbon-carbon. These are going to be your sp hybridized orbitals. So this one is going to actually bond to your hydrogen. Same thing on this side, that's going to be your hydrogen. And then these ones will eventually overlap and create your sigma bond there. But then you can see that we actually have 2 different orbitals. I'm just going to highlight these in different colors. So you have these ones here in red, and then in the rear you have this one, and you have this one, and this one. So what's going to happen is that these ones are going to bond. That's going to be your double bond. And then these ones are also going to bond, and that's going to be your triple bond. So you can see that your sigma bond is already existing there, and then you have 2 pi bonds. You have one over here, okay, and then one over here, and they're occurring above the actual sigma bond itself. So let's look about benzene. Benzene is an important molecule when it comes to organic chemistry. When we look at benzene, we try to figure out the hybridization. Again, we look at the electron domain. So for each carbon, it has 1, 2, and 3. Remember that a double bond also counts as just one domain. So 1, 2, 3 means it's going to be sp2 hybridized, and it's also going to have a trigonal planar shape, which is going to be at 120 degrees approximately. And when we look at this, we also see that it has a double bond. Now, if it has a double bond, that means that it's going to have, each carbon is going to have an unhybridized p orbital. So when we look at that, again, our structure is going to be like this. we have our sp2 hybridized orbitals. So one for one carbon, one for the other carbon, one for the hydrogen, and then this is going to be the p orbitals. And you can see that that structure kind of looks like this. Here are all the sigma bonds that are occurring. So there's 1 bond, 2 bond, 3 bond. Those are your 3 sp2 hybridized orbitals. And then this one is where your p orbitals are going to be. Now, an interesting thing happens. When you have these p orbitals that are above and below, you actually have electrons that are able to move from one to the other. So when we look at benzene, we've seen this before, where the structure, you can see the double bonds are here, the structure can change from here to here to here, and they can keep moving around and around, and that's because the electrons can actually move from one orbital to the next and keep going around and around and around and around and around. And eventually what's going to happen, as they keep moving around and around and around, you're going to start seeing this kind of circle form, and you're going to get that. Now the same thing happens on the bottom side as well. So you're going to have kind of two donuts being formed on the top. And this is the reason why sometimes you see benzene represented as a circle, because that circle over here represents the double bonds that are delocalized. They're not going to be here, here, or here, or here, here, here for any prolonged period of time. They're going to keep moving around and around. And so again, here, if we were to just kind of take a still frame, you can see that these would be our pi bonds available on that side or on that side. But again, we know that these are going to be moving around and around, so we get this kind of donut shape that occurs over here. And again, that's the delocalized electrons, that it just keeps moving around from one p orbital to the next. And that's also the reason why benzene is a stable molecule, because that delocalized electron movement allows for that little bit more stability. So thanks very much for watching. See you soon.